Hello everyone. Hello everyone. This video I'm going to talk about a projectile motion, and projectile motion is a famous 2D motion. And projectile motion pretty much is an object launched into air and then moves predominantly under the influence of gravity. Okay, if you like a baseball, hitting a baseball and shooting a basketball or launching a missile or inkjet paper, inkjet print, or not inkjet paper, inkjet printer when he has to print, he had to inject the ink. Okay, inject the ink. It's a projectile motion. Okay, it's really a projectile motion in inkjet printers. Okay, and for projectile motion, for now we are pretty much simplify the projectile motion because we don't consider air resistance. Yeah, for small object, for small object, we don't really need to consider the air resistance. But if you have large mass, but something like a missile or rocket, you have to consider air resistance. Okay, or very light in some like a leather. You also have to consider air resistance. Okay, for now, our problem we don't consider air resistance right now. Okay, and then for the projectile motion, we just same thing. We just use equation of motion, two-dimensional equation of motion, and use the component language to solve the problem. Okay, so for projectile motion, I know the textbook give you lots of formula, but I don't think you need to memorize any one of them because they are all from the equation of motion. So let me show you some of formula. I won't demonstrate all formula in textbook. I just show some formula for you, and then just one example question. I think that should be enough for the projectile motion section. Okay, for the projectile motion, one thing we're interesting about is the flying time. Okay, flying time. The flying time means how long if you launch an object and its angle is theta relative to the horizontal axis. You launch the object and when will it land? When will it land? When will it land on the ground? Okay, that's the time. Okay, another thing we are interested in, what's the maximum height? Maximum height on the projectile motion. And for this problem, yeah, we just use the equation of motion. We can get that. Okay, the first one is flying time. Okay, flying time for projectile motion. The first one is flying time. Okay, flying time. Yeah, and for problem, we just use y component. Oh, sorry, no. We just write down all of them. Okay. Let me write down the equation of motion. Initial x component times t plus 1 over a, or 1 over 2, and a x t squared, and y equals yi plus vi y component times t plus 1 over 2 a y t squared. Okay, what's flying time? When will it land? Okay, so for this problem, when will it land? When will it land? Let me draw a small picture. Okay, this is the v is initial velocity theta. Okay, when will it land? When will it land? Okay, want to find out when will it land. Okay, when the object lands on the ground, that means its coordinate of y component is 0. Okay, and since we set the origin here, so our initial position, initial y component is also 0. Okay, and our initial velocity in y component is v. Let's just say it's v sine theta. Okay, I should. Okay, and what's the acceleration of y direction? And then in this coordinate setup, and acceleration is always points downward with g value. So it's downward, so it's negative. So AY is minus 9.8. So pretty much have everything. So plug in there, 0 equal to 0 plus V sine theta times t. T is our flying time. I just don't want to write it fly here. It's very complicated. And minus 1 over 2 times 9.8 and t square. So what will we have? I shouldn't use 9.8. Let me use the G. Okay. Let me use the G. Let me use G. Let me use G. Okay. If we don't have, I don't have a number in there. Okay. So for this one, we will what we will get? We get the so okay. We have V sine theta t minus 1 over gt squared equal to 0. So we factor t out. V sine theta minus 1 over 2 gt 0. So we want to find out the t flying time. So this two we can get the solution. One is t equal to 0. The other is gt over 2 equal to v sine theta. So t is 2g v sine theta. Okay, we have two answers. One is t equal to 0. One is v sine theta over 2g. Okay, the reasonable answer is this one. Because for the other answer, 0 means the origin. Okay, in the origin, is y component also 0? Yes, but that's not the answer we want. We want the answer here. Okay, the landing time. So it's v sine theta over tg. So since it's the his flying time is v sine theta over tg. So what's the x range? That means it's xf. Okay. What's xf? Okay, xf we don't know. So xf we just write it here. The initial position of x 0. Okay, the initial position of x component v cosine theta, and the flying time is v sine theta over 2g. Okay, and acceleration of x component, because in this projectile motion we only have suffered the gravity. Only y component has acceleration. X component, it doesn't have any acceleration. So this is 0. So that's your f, the horizontal range. Okay, that's pretty much about. Okay, using equation of motion, you can solve the flying time and the horizontal range, and you don't have to memorize any formula. And another interesting question we want to ask is maximum height. Maximum height. Okay, maximum height is here. Maximum height. And I will show you also we can use equation of motion to solve the maximum height. And for the maximum height, I have to erase the screen. So if you want to take a note, just stop here, and I have to move forward. Okay, so just run this really, or maybe I'll clean up from. Okay, I'm gonna clean back one here. Okay. Yeah, because we just want to use the same equation of motion. Okay, so what's the maximum height? Okay, maximum height. Okay, so maximum height. Maximum height. Sorry. Okay, maximum. Okay, height. Okay, maximum height. We pretty much we have to use the equation of motion of y direction. Okay, so equation of motion is y direction. Okay, so as we know, we have the same setup. So pretty much YF. Okay, because we want to find the maximum height. So YF. Now, what's the YF? I don't know. So okay, initial position is 0, and initial velocity at y component is v sine theta, right? And times t plus 1 over 2, and it's minus g t squared. So we will see. Let's see. Our y component is a function of t. Don't you can you see that? Okay, our y is function position of y is function of t, and we want to find the maximum of this function. So for this problem, actually we can use calculus. Okay, in calculus, maybe you will learn this in this semester, but I will just show it. I'll just show you the conclusion. If there's a function, there's a function, let's say it's a function of x, we try to find the extreme value, extreme value. Okay, we can use the derivative. Okay, if we find the extreme value of the function on x coordinate, so first of all, its first derivative must be 0. And we can split it into if maximum, minimum, because maximum and minimum, they all extreme value. Okay, one is maximum, the other minimum. Okay, but when they have the same, the first condition is no matter maximum, minimum, the first derivative must be 0. And if you maximum, your second derivative is less than 0. And the minimum, so your second derivative must be greater than 0. Okay, that's the calculus. And we can use calculus to solve this problem because we want to find the maximum height, maximum of y. Okay, maximum of y. So we adapt this a little calculus. So we do the derivative with respect to t because we are a function of t. Okay, so the simple for a derivative of power function, I've shown in class, so I don't want to address it anymore. So minus gt equal to, and for extreme value, extreme value, no matter minimum or maximum, is 0. So we can find when t is equal to v sine theta over g. Yeah, when t is this value, y has maximum. Okay, and for maximum, I think I will. Yeah, I forgot. I should check the second derivative of t. Is that less than 0? Yeah, we do it more time. If you do a second derivative, just to do the derivative one more time. Just do the v sine theta or minus gt. Just do this derivative one more time. We get the minus g, so it's less than 0. That's why. Okay, when t is equal to v sine theta over g, that's maximum. Okay, so, and what's the value of the maximum? Okay, what's the value of maximum? Okay, I just erase the first part out. Okay, what's the value of the maximum? Okay, we already find when t is equal v sine theta over g, the y has maximum. So we'll just plug the value in there. So, so yf maximum is when t equals v sine theta over g. So yf is, so it looks like ugly. Just plug g in there. Just plug g without split. Plug time in there. G v sine theta minus g over 2 g v sine theta square. Okay, that's pretty much about formula, but in textbook they will arrange this, make it more nicely, more beautiful. Okay, but it's the same. I believe it's the same. Okay, that's pretty much show you how to use equation motion to deal with the projectile motion. Yeah, and next video I'm going to show you one example, another example for projectile motion, and that's pretty much this section. Okay, that's most about 2D motion. Okay, see you next video. Okay, bye bye. Ah, over here.